So here we have a half-pound block and it's released from A and it slides without friction along the plane. Calculate the force of the plane on the block at B and C. So let's start by drawing our free body diagram at our position B. So at B, we're going to have our block. It's going to look like so. And we'll draw over here our kinetic. So here's our free body diagram, and here's our kinetic diagram. So at B, we know that we're going to have a weight force pulling down. So we'll just say W. And we're going to have a force, our normal force, on the block, N. And this is at an angle. So this is going to be a 60-degree angle here. And for our kinetic diagram, we can say we're going to have our normal and tangential coordinate system here. So we're going to say mass times our normal acceleration and mass times our tangential acceleration down here. And that's just going to be equal to mass times v squared over rho. And this will be equal to mass times v dot. So there is our kinetic and free body diagrams. So let's start now by analyzing B. So the sum of the forces in our normal direction is going to be equal to mass times our acceleration in the normal. And this is going to be, we're going to assume here that here's our positive, and then we're also going to use this direction as our positive for our tangential calculations, which we'll write down here. So if we take the sum of the forces for our normal, we'll have our positive normal force minus our weight times the cosine of 60 degrees. And that's going to equal mass times v squared over rho. And in our tangential, when we look at the sum of our forces, we're going to have our weight times the sine of 60 degrees. We can rearrange these variables to say n equals m v squared over rho plus w cosine of 60 mass times v squared at b over rho plus w cosine of 60 degrees equals our normal force. So to use VB, we're going to have to use our work energy equation that we introduced last time. So let's look now at our different states between 1 and 2. So at state 1, we're going to start from rest. So we can say our kinetic energy equals 0 because we're not moving. And our elastic energy is going to be equal to 0 because there's no spring or anything involved in this problem. But because we're, at a height off the ground, we're going to have a potential energy. And we know our potential energy equals mass times gravity times height at our state 1. And our height at state 1 from our origin that we drew over here, we can see is 4 feet. So we can just call our potential energy, for now, we'll just say 4 mg. So at state 2, we know kinetic energy. We know the equation is 1/2 mvb squared. Our potential energy at state 2 is going to be equal to negative mgh, because we're going to be below our origin, our datum line, if this is our datum. So we're going to be negative. And our height here, we can just call it 3 sine of 30 degrees. So that H2 that's drawn, we're just going to use our geometry here. So we'll just write for now 3 sine of 30 degrees times negative mg. And of course, our elastic energy at 2 is also going to be equal to 0. So what is the work done now? So if we look at our work energy equation, the energy at 1 plus the work from 1 to 2 equals the energy at 2. You know, we've defined our energies here, so we want to plug in 4 mg plus 0 plus 0. So our potential energy at 1, we have 4 mg, and we have 0 kinetic energy and 0 elastic, plus our work from 1 to 2 equals negative mg times 3 sine of 30 degrees plus 1/2 mvb squared plus 0. So on this side of the equation, we have our potential energy, our kinetic energy, and our elastic energy. So this is a smooth, frictionless surface, so we're not going to have any work done. Now let's use our conservation of energy to solve. So let's start plugging in. So 4 times 1/2 pound, mass times gravity, is going to be equal to negative 0.5 times 3 sine of 30 degrees plus 1/2. We're going to take our mass, so we're going to say English unit problem, 0.5 divided by 32.2. That's going to give us our mass times VB squared. And that'll allow us to solve for VB, which is going to be equal to 18.8 feet per second. So if we plug VB now into N, we can say N equals 2.08 pounds. And that's just using our equation for N up here, plugging in our new VB value. So now we can look at the block at C. So at C, our block is going to look like this. And our kinetic diagram is going to be, again, in our normal tangential. We can say mass times AM equals MVC squared over rho. And in our tangential, we're going to have mass times V dot for our kinetic. And our free body is going to have our normal force pointing up and our weight pointing down. So let's take our equation of motion now. So the sum of the forces in the normal direction are going to be equal to mass times acceleration in the normal. Our normal force minus our weight equals our mass times VC squared over rho. So let's get another equation here for N. So N equals W plus MVC squared over rho. So like at B, we're going to use this equation to solve. So again, let's use our work energy equation from A to C. So at A, or we'll just call this 1 and 2 again. So at 1, our kinetic energy is going to be equal to 0 because we're starting from rest. Our elastic energy is going to be equal to 0 because we have no springs. And our potential energy we will have, so let's just call that for now MGHY. H1. And at state 2, so at point C, our kinetic energy is going to be equal to 1/2 mvc squared. Our elastic energy at 2 equals 0. And our potential energy at 2, we're going to have mass times gravity times a negative height, because again, we're below our datum. So now, when we're looking again at our work energy equation, we're going to have no work done between 1 and 2, because again, it's a frictionless plane, so no work is going to be done. So let's plug in and solve. So that is going to allow us to write mg h1, so our potential energy at 1, plus 0, because we have no kinetic or elastic, equals negative mg h2 plus 0 for our elastic energy at state 2, plus 1/2 mvc squared. So we can say, if we want to solve for just VC, that'll allow us to write 2 times gravity times H1 plus H2. So if we know that H1 equals 4, H2 equals 3 feet, that's going to allow us to just plug in, and that'll give us VC equals 21.2 feet per second. And then if we plug VC in up here, we'll get a normal force at C of 2.83 pounds. Thank you for watching. If you like this video, please be sure to give it a thumbs up and subscribe. That really helps support my channel and helps me continue making videos for you guys. I'll see you next time.